Before we move on to talk about interaction, other ways of interaction between two or more waves, let's talk about this phenomena called diffraction. Okay, so what is diffraction? We know that light travel in a straight line. What if they meet an obstacle or an aperture? So this is what is going to happen. You can see that the wave actually got diffracted into different direction, as in they are not anymore in a straight line. Okay, so just like the example here, real example that I took this picture in 2009. Okay, on the way back, but don't do that. I'm driving at a traffic light, so I took this picture. Diffraction, very nice. So diffraction is a wave phenomena where, I mean, this is the definition. You must know how to describe that. Where a wave spread out, okay, into the geometrical shadow, okay, and it will be more significant if the aperture size is the same as the wavelength of the incident wave, or smaller than that. Okay, so this is the geometry. So here is the shadow of it, geometrical shadow. Okay, so here's the shadow. Yeah, so the wave come from here, and then it pass through this aperture here. Okay, and instead of just going straight, it's now spread out like this. Okay, spread out to where? Spread out to the geometrical shadow. That's how it's spread out. So this is the one that I'm drawing here is a significant one. You can see it's like a curve, a nice curve like that. What if the opening is too big? The opening, as in this size here, is too big, very much bigger compared to the wavelength. So what you see here is the wave fronts. Distance between the two wave fronts is the wavelength. So compared to the separation here, this L, is too big, then it won't be nice. I mean, the diffraction is not significant. So it's like you see some parallel lines going through, wave fronts just pass through like that, like ordinary. Okay, so the spread out is not really very serious. Okay, so practice drawing this, because it once, I mean, it come out like a few times that you need to draw, and they give you 2 or 3 marks. Okay, so now I'm going to show you an animation showing this effect. Yeah, hold on. So again, this is a fat simulation. What I have here is the water wave. Okay, so you see on the screen here is a water wave. I can't draw on it. Actually, I can, but never mind. The water wave generator. You just follow my pointer there. Water wave generator. Okay, so I already switch on and I generate the wave, and then I put a slit in the middle here where I can move about. Okay, so when I play that and it's passed through the slit, and then you get the diffraction like we mentioned just now. Okay, so I already set the slit width into about the size of the wavelength. So size of the wavelength is like the you see the blue color here, that is actually the wave fronts, right? So between the two wave fronts there, that's the wavelength, and it's about same as the slit width here. So just now we say that if this slit width is about equal, then the diffraction is nice, just like the example shown here. Okay, it's spread out. So what if the slit size is like very big? Okay, say like this. So let me play the animation. Okay, so you can see that in front here, though the wavelength is still maintained the same and the frequency maintained the same, but you can see that the diffraction is not so serious now. Okay, you can look at the geometrical shadow. It's just a little bit compared to when it is very much smaller. So I now reduce that. So what happens if I reduce it to even smaller than the wavelength? So you can see that the diffraction pattern is still significant and is still very nice. All right, go back to that. On a water wave, we can actually see very easily, because if you are using a ripple tank, then it will be easily observed. how the water spread out. But let's say you're using light, then you really cannot detect when it is moving across a region. You only see when it get reflected or achieve at the arrive at the board and get reflected, right? So so we can place a screen in front of that, and then we look at how the light intensity behave. So when we have the wider slit, as in less diffraction, then the central maxima, this one here, will be less compared to the one that has a greater diffraction due to a smaller width there. Okay, so let's look at the animation. Alright, what I have here is just to simulate the one that we said just now. So we have the slit width set to about the size of the wavelength, and because it's a light, right, so we can't see that. Animation, of course, they'll show the colors here. So we put a screen, okay, and also I show a graph here, the intensity graph. Okay, this one is supposed to be greater one because the diffraction should be big for this. So if I increase the slit width so that the diffraction is less, then you can see that this graph, the center here, it will go up, yes, but the overall spread of the graph, right, it will shrink. Okay, instead of spreading out like this, then it will shrink. Okay, let's see. Okay, so then you can see that it gets focused. Okay, it gets focused more, less light is at the side there. Okay, so when I move to a smaller one, then you can see that though the intensity now reduced at the middle there, but they spread to a bigger region. Okay, that's how light will behave. Okay, so once we have understood regarding the phenomena of diffraction, what if now we have two slit? Okay, we have two slit. Would it, I mean, this one would never happen, right? The slit just, I mean, the wave just passed through. Just now we know that diffraction causes it to get diffracted and spread out and bend, right? So meaning that the waves now, they will interact and overlap. That's where it starts to get interesting, because it will be like this. Okay, it will form this pattern, and we call that the interference pattern. Okay, when you see this, it's called the interference pattern. Okay, where the waves interfere. So to get the nice picture just now on the pattern just now, first of all, you must make sure that you have coherent wave source. So understand this concept, it's very important. Coherent wave source. That means the source where the wave come from, they must be coherent. All right, so you should ask, what is coherent then? So coherent means the two sources have a constant phase difference. Constant phase difference. They have phase difference, but it's constant. Okay, they might not have phase difference, but it must be consistently not having phase difference. Okay, so give some example. If the phase difference between two sources as they emit the wave is 90 degrees, then it must be 90 degrees throughout time. If the phase difference is 0, then let's make sure that these two sources, the phase difference is 0 throughout time. Okay, and so to other instances. So I give you some picture here to illustrate what is coherent. This one that you see at the top here, there are actually two coherent wave source, because you can see that it's consistently 180 degrees out of phase, or pi radian out of phase, right? Whereas at the bottom here, you can see the one that's highlighted here, there's some abrupt changes. And so this one is already good enough, or enough to cause the two source to be categorized as not coherent. Okay, not coherent meaning that you are not going to get a nice interference pattern. All right, let's try. Okay, the one at the top or the one at the bottom here are coherent sources. Very significant, right? This one is like very obvious. Okay, there are some changes here and there, so this is not a good one. Not a good one means are not going to produce a nice interference pattern. Okay, whereas the top one is consistently about pi radian maybe. Okay, so they produce interference pattern like I mentioned just now. This kind of picture is what you always see in a pond or on the surface of water. Okay, so interference pattern happens is because, like we say just now, due to diffraction, the two or more waves that overlaps, and then you get a resultant wave. That the amplitude of this resultant wave, right, is given by the principle of superposition. Okay, we can. I mean, we are only interested in the amplitude. That's good enough. So if you want to get an observable interference pattern, like we said just now, the first point is the sources must be coherent. This is okay. We already understood that. Check. Okay. Secondly, they must have roughly the same amplitude. Imagine they are not having the same amplitude, right? When we talk about the principle of superposition, if you want them to completely cancel off, but one is having like 3 cm as the amplitude, one is having the opposite side of 1 cm amplitude. So 3 cm, 1 cm, how do you get a 0 there? 3 minus 1 at most is 2 cm. So you wouldn't get a nice, completely destructive point there. And then if it's a transverse wave, then that must be in the same plane. Okay, so what is actually same plane means? Let me take something to demonstrate to you. Okay, so I have two planes here. Don't tell my son. So imagine that there are some waves on this plane, and there's another transverse wave on this plane. So if I want these two to produce an interference pattern, so I cannot do like that. Okay, I cannot do like that. I must make sure that they are exactly at the same plane. Okay, from the side view is like this. So it must be exactly at the same plane. Alright, so like this is called the same plane. Okay, so constructive and destructive interference, if you want to get, I mean, if you have an interference pattern, then it is actually, it must consist of region of maxima and minima. If one pattern only, that's not considered. You cannot just have one maxima or just have constructive interference, or you cannot have an interference pattern that only have a destructive interference. You must have both of them, then only is called an interference pattern. Let's look at some example where we can have interference pattern. The first one is we have two source interference pattern that form in a ripple tank where there's two dipper in the water, and then you see this kind of pattern here. Okay, where you see this kind of pattern. So later I'll show you the animation. Let's skip this one. And sound wave we can also have. We have two speaker, then we can generate the interference pattern. Microwave also can. Okay, but microwave, because we cannot see the microwave as mentioned earlier, right? And the sound also. So microwave, you need a detector to show you. So the detector is connected to a microammeter. Therefore, as you move it along the x, right? So I mean the y and the y prime, you get like the 0 reading, maximum reading, 0 reading, maximum reading, 0 reading. Okay, so later in the animation when I show you, then you understand it more. Okay. Okay, I have the example of the ripple tank just now, where you have two dipper. That's the same thing as opening two hole at the barrier here. That's the same thing as two source. Yeah. So you can see this pattern as the constructive and destructive interference. So we have minima and maxima. The line that is a bit blur here actually is called the region of minima, because if you look at the graph there, or the readout there, this is actually very small as I move along that line. So this is where all the waves are, the two waves are cancelling out, whereas this region here, where it's a bit broader, okay, you can see that the reading is very big. This region is very big. This region is very big. So in between them, there's a border where it is along that is a destructive interference. Okay. You see the same thing when I change to a two speaker as a sound generator. So it's like two speaker here. Then you actually see the same region where there's a blur line that is indicating the minima there, and then we have the broader region where there's a maxima, okay, where they interfere constructively. All right. When it comes to light, it's slightly different again because like we say just now, we cannot see them, so we can only put it on the screen and then you can see this kind of region. So we have the black color region here, which is the destructive interference, which is exactly along the line of the blur line just now, and then we have the bright spot here, which is the constructive interference, or we call them maxima. So next we're going to go in more details into this, huh? Okay, I'll see you in the next video.